Dear students, so today we will go for chapter number 5 in big data storage concepts. So what we will go study in this chapter, we will study about the different concepts of storages in a databases, and we will see that what are the processes in the traditional basis and what are the rules regulation in the traditional databases. Like they contain a property which is called ACID, ACID, while in the big data they maintain a property which is called base, BASE, right? So ACID is like stands for atomicity, consistency, I for integrity, and D for durability. While the base, it stands for basically available, and then E for eventually, and eventually consistent, right? So we will see now these properties of the big data storage concepts and see that what are the internal concepts in it. So initially, we will see some symbols that is particularly used in a big data. Like for example, for cluster, this kind of symbol is used. So whenever you see this kind of symbol, so this is used for clusters. So cluster is basically a combination of processors, and or the combination of the memories. So when you combine memories and processors, so that becomes the clusters. For file system, if you see this kind of symbol, so this is used for a file system. So this is a very generic symbols for it. Yeah, for distributed system, when your operating system is distributed, or when your data is distributed across multiple processor or across multiple storage devices, so the symbol which is used for it is similar like it. So if you see over here, these two symbols are combined. So the cluster symbol plus the file symbol, when you combine these two, so you get this new symbol. So here we see over here that we have like an SQL like structure, and which is used in a big data. And for big data, we cannot use the normal SQL. We need to use a special SQL that is called NoSQL, or not only SQL, and it has an API, and it can be controlled with the Hadoop, or it can be controlled with the Cloudera or Apache. So there is a system, for example, in as we know that in big data, the high velocity, high volume, and high variety is a problem. So what we do we do shredding. We divide the data into different data sets. Like this one big data set is divided into two. For example, it has for example, 4 rows. So instead of four, let's suppose it is 4,000 rows. So 2,000 rows we keep in one server, and the rest of the 2,000 rows we keep in another server. So this is symbolically I'm telling 2,000. So here it is 4 rows only, but it could be 4,000, or it could be 4 million rows as well. So by this way we are sharing the load on the different servers. This is another example for shredding, where data is fetched from both node A and node B. So different user, they are fetching the data from different node. So whenever we are accessing YouTube or Facebook or Instagram, so maybe two people sitting in one room, or two brothers sitting in one room, they might be accessing different servers. Okay, so the same data could be accessed from the different servers. The same video could be accessed from different servers. Then there's for a fault tolerance, or to keep the data alive so that we could not lose the data, we do the replication, or we do the backup. So one or similar data, one data can be replicated into two different data over there. So this is the same data is replicated, so that in case of one failure of the data processing occurs, then we can have the backup system. Okay, there's another scheme which is called master slave. So in the master, usually the people they can have reading from the slave. Okay, because reading is is a harmless process. So if you read it, so it's a harmless process. But if you write it, when you change it, write means when you change the data, then you need to do in a master copy. So if you do in the master copy, automatically it is transferred to the slave's copy, right? But while reading is like normal when you fetch the data, if you do like select static from EMP or select static from department table, so that is like harmless operation, so you can do it from the slave. But if you want to change it, so you cannot change directly into the slave, you must do in the master. So there is another example that of master slave replication where read inconsistency occurs. So sometimes there could be inconsistency, and when there is an updation in the master slave, so maybe the data in the master is different and in the slave is different. So when you read it, the data from the slave, so it could not be updated one. So that is called inconsistency. So when the data is different in the master and in the slave is different, then read inconsistency might occur. There is also like another way which we call like pairs. So if the data is divided into replicas and they're all like connected as a pair, so we can have like we can read it and we can write it from any pair. Okay, so you can see over here replica A, and we have replica B and replica C. So what happens is writes are copied to pair A, B, and C. Simultaneously, data is read from A, but it can also be read from B and C, right? So here there is no like priority. Okay, so replication is also an example of peer-to-peer replication where the inconsistency read occurs. So in case of like when you make some changes, when you update the data in, for example, in replica A and B, but if your replication is not being done in the C, in that case, if some other users they read it from replica C, that could be like read inconsistency, or we can say like loss the old data you access, not the new data. So here in this one, in the comparison of like shredding, so here we have combined the shredding. So here the data is divided into two parts. If you see over here, the data is divided into like shredded as well. This like these two records are here, and these two records are in this one, right? So if you look over here, it is shredded, and here is the replication. Okay, the full data is replicated here, and another as a node here. So this is an example of shredding and replication together. And here is the example of show the combination of shredding and master slave. So how we can do the master slave and shredding both. So here you can see shredder has been occurred, and there is also a combination of master and slave. So in master and slave, we do the writing, we do the updation in the master, and in the slave we just do the reading, means like fetching the data only. But if you alter the data, if you update the data, if you insert the data, you must do in the master node. And this is an example of shredding and peer-to-peer. So we have some different combinations for different one. So in the peer-to-peer, like read and write, there is like no priority. You can do the read and write in any pair. Consistency, all the three users get the same value for the mount columns, even though their three different nodes are serving the record, right? So like for example, there are three users and they are getting the data from three different devices. So in that case, like everyone is getting the same data, so that is called consistency. Okay, then we have like availability and partition tolerance. So sometime when like there is inconsistency and the partition has not been updated, that in that case might be your user cannot update it the new value over there. So availability and partition tolerance is very important. And in case of any failures, requests from both users are still served from, for example, for 1 and 2. And then with the user B, the update failed as a record with ID number 3 because it has not been updated and it has not been copied over to the city or to the PRC. The user is duly notified that update has been failed. So in that case, this must be notified. If you see over here, just to re-explain for you, like here, because the update has not been done and the operation has been failed. But while here, the operation has been successfully done. So that the data has been inserted, the insert command has been working well like we do in common SQL, but here the update command is not being done, so it has been failed over here. So this is called availability and partition tolerance. Yeah, we have then CAP theorem. So CAP theorem means like we need to keep the consistency, we need to keep the availability of the databases. The consistency means the data should be like consistent from one state to another state. and partition tolerance. When there is a partition, so the data must be consistent across all the partitions. Yeah, then we have two important theorems, or the properties on the database. So one is called ACID. So ACID, as I told you, that ACID means like atomicity. Atomicity means that either the transaction has been successfully done or not done. So there is no middle stage in between that one. Consistency means like, the transaction has been successfully performed, and the data is consistent across all the pairs. And then we have like, isolation. Isolation means that if you have multiple transactions, every transaction is separate, like, they are isolated from each other, so there is no interference between transaction to transaction. And then we have durability. Durability means that even if there is a failure in a power, so either it will go to the old consistent state or to the new consistent state. So if, for example, if the ATM machine fails, so either you will get the money or you will not get the money, but the money will not be deducted from your account in case if the transaction get fails. And then for the big data, we have the different like rule that is called base. So in the base, what we have it in the base, when you have a big data, it means that it should be available, basically available. The data should be basically available 24/7 for you. Okay, but there is a stage which is called soft state. Soft state means that temporarily the value might not be updated, but after some time it could be updated, or maybe the old values is removed after some time. Maybe after 10 days the old data has been removed and replaced by the new data. That's called soft state. So it takes the time. And then we have eventually consistency. Eventually consistency means at the end, means like after 10 days or somehow you will get the consistent result, means the data would be same, there will be no corruption in that one. So here I have some examples for you. There is a one example. If you look at here, yeah, ACID properties. This is the ACID property. So the entire transaction take place at once or doesn't happen. Consistency means that database must be consistent before and after the transaction. Isolation means multiple transactions occur independently without any interference. And durability means the changes of successful transaction occurs even if the system fails. Okay, for the big data, this is a comparison. So for the big data, properties are more relaxed version of the ACID that trade off some consistency is guaranteed for the greater scalability and availability. So the main problem here in the big data is that we need more scalability, more availability because of the huge size. And then we have like base only requires eventual consistency, not the immediate consistency like the normal databases we have it. And this one is more suitable for large scale and highly available system, while ACID property is for the traditional databases. So this is all about like, the normal traditional databases and for the big databases. So thank you very much and see you in the class. Thank you.